Hello everyone, I am Dr. Jayasingh, coordinator of CE201C subject, and this is another video lecture, and this video lecture will cover about analysis of stress in 2D case. And of course, when you come up with like a 2D stress analysis, so we going to narrow down to our problem to plane stress problem. So from last video lecture, you realize the definition of what is the definition of plane stress problem. Of course, in here also I will give very brief definition for plane stress problem. So now we can shift to plane stress problem. Before you jump to this problem, plane stress problem, I will go our past knowledge. So I will take this one. So this CE201 series, lecture series, we mainly focus about beam problems, beams. Okay, so when you come to the beam, of course we are working with like a uniform or otherwise like a symmetric beam arrangement. Okay, first we try to understand the beam system, and after that we try to find external reaction and external reaction means like a reaction force of the supports. I try to solve this one from the using equilibrium equation. Of course, you know this one from GP110. And after that, we develop the bending moment and shear force diagram. You know already this bending moment and shear force means internal reaction force. So internal reaction of when you come to the internal reaction, of course there is some other part, bending moment, shear force, of course there are axial force, and there are we call torque or twisting moment also. Of course this one we will learn later under torque or twisting moment. Final one, of course, the final section of the CE201C. This axial force, of course, we are not going to work on this one, but really it is nothing the very straightforward things. So we mainly focus in here the moments and shear force. So first we try to understand external force and we find that one, and after that we develop bending moment and shear force for target beam arrangement. And after that what we realize, of course, due to this bending moment and shear force, there we can see stresses. Due to bending moment we can see the normal stresses. Due to shear force, what we can see the tau component, that means like a shear stress component. And last few lecture we try to understand variation of these two stresses across the beam cross section. Okay, symmetric beam cross section. So if you have like this kind of arrangement, cross section like rectangle, then you realize, of course, stress variation like normal stress varying like this, depend on your loading arrangement, and your shear stress going to vary like this. So that means now we know the variation across the beam section. Okay, and keep it in mind, so this is we call very general cut. General cut means like we are coming here, we are getting the vertical cut. Okay, this is vertical cut. Now any layer or any point of this any point actually or any layer, you know the normal stress and shear stress. Actually along this one, normal stress or shear stress are going to vary. That means any point stress you can define. So when you come to this one, now you know when we are going to interpret the stress in point, what we are actually using the element, rectangle or square element. Okay, this is actually going to represent this point. Okay, point is stress. Okay, so from last lecture we realized, okay, there is a force element, we call this stress element, and we can represent stresses. So at that time we represent the stress situation for this general cut. This general cut means this vertical cut. Now what we going to do, actually what we going to do, we going to check if we have any inclined cut, what going to happen to these stresses? Now if I have like a vertical cut like this, you can see normally stress this, I will put x, and here is stress like something tau tau xy. Okay, this is for your Cartesian general Cartesian coordinate system. Okay, now in this one, what we are going to do, this is a point. Okay, what we are going to do now, we are going to check if we are going to rotate this plane. Okay, now you can define again tau x dash, actual different one, and so sorry, sigma x dash and tau xy dash. So what are those values? What are those values, and how is going to vary with this angle theta? Angle theta. Yes, you need to keep in mind, this is something, of course, if you have trouble with interpret this stress. Okay, stress, this is of course equal to something like here, keep it this type of example. So if we're going to shift this kind of example, keep it like, think about like this is some point, we can see so much of forces. Think about F1, F2, F3, F4 forces. Now what you can do it from this A level, you know this one, so you can resolve, or you can find the component or resolve for this all forces for this direction, or you can find Fy and Fx, and you can get, of course, from this one you can finally you can get the resultant force also. Okay, R also. And similar, of course, you can use this axis system, but some any other one, if anyone like in this kind of arrangement, okay, I will use another color, so blue color. So if anyone like to resolve these forces in this way, okay, this is x dash and y dash, of course he or she can also resolve that way. But these values, now think about like this, f1, fy dash and fy is not going to equal, and this is also same, not going to equal. But keep in mind, this resultant is not going to change. Okay, resultant force is same, but these component going to change. Same thing actually happening here. For the resultant of this point, it's same. It's not going to change. But the component we call in here very special names, no? In the with with parallel to this cutting plane, we call this one shear stress. Perpendicular component we call normal stresses. Those components going to change. Okay, that's the only thing. Those components are going to change with this theta. We are going to understand or study with theta how it's going to change. Very simple now. How it's going to change, and where we can see the maxima, where we can see the minimums. Why we are worried about those things? Because if we can see the maximum something, at that time actually we can observe the failure of system, or failure or fracture or cracks of the system, or your target metal sample or metal or material sample. Okay, now try to get the idea. We are starting from here, we narrow down to beam, and we start to find out like internal reaction. In here there are 4 type main internal, but we focus mainly about shear force and bending moment. After that we realize, of course, bending moment and shear force cause shear stress and normal stresses, and we last actually 2 video lecture, we try to understand the variation of these shear stress and normal stress across these beam sections. And finally, now we going to go more detail and more depth about these stresses. Now we're going to, of course, we have now point wise, we know for general vertical cut how are these stresses, but how about the any angle type cutting, or how about with the theta, rotation theta is going to vary. That's the things in this special special session we're going to cover. And here again we're going to work with plane stress problem. There are mainly, when you come to the 2D problem, 2D we can work with like a plane stress or stress or plane strain. So in here 201C or 201 C201, we are generally working with plane stress problem. Yes, I will upload some reading material for plane strain problem. If you have like a plane strain type problem, how you need to analyze. But actually, I'm not going to test this plane strain problem. Okay, so but in the future, of course, you need this knowledge for your engineering problems. Okay, in here we are going to target about plane stress problem. Now we will shift to plane stress problem. Okay. So this is plane stress problem. This is plane stress problem. So this is of course the last video lecture also I explained about this one. Now you can get clear idea about this one. Think about this kind of simple beam arrangement, simple support beams, and I am applying load in here. In here we are not applying any axial forces. Okay, we are not applying axial forces. Of course you can apply, but here we are not going to apply. And here if you get to cut any small element, otherwise actually this is one point. Okay, one point is stresses. If you're going to think about point stress of this system, so what we can see actually is normal stress that align with beam axis and shear stress. And we are not going to apply, this is a 2D case, we are not going to apply any force in perpendicular this direction. Because of that, we cannot see any stresses that coming out from this plane. Okay, so the definition is so simple. These kind of arrangement we can see only plane stress. Only one plane we can see the stress, others are, of course, strain can come out. Okay, this problem plane stress problem, plane strain can come out from the plane, but stresses cannot come out from the plane. Sorry. Okay, and this is we call the plane stress arrangement. And when you come to this kind of torque, of course we can put the here torque, and of course I am applying the axial force also. If we know axial force, then we cannot see axial component, only we can see this shear arrangement only. Of course we will discuss this arrangement under torsion or twisting moment later, but in this one also we can see only our stresses we can see in one plane, out of plane 0. So again this is we can consider as a plane stress problem. So this is a definition. Of course this what we are already we know this one. And when you come to this one, this statement, stay of the plane stress edges of the rectangle element in which there are no stress normal to its face, called the plane stress. This definition you already know. So now you can go to like a matrix arrangement. This also from last lecture you already know, but I am applying to complete this session. And this is 3D case, our 3D cube stress element. We can see all 9 components here. What we are interested when we are coming to plane stress problem, out of plane stresses we need to put to 0. And the first, of course, we need to define our plane. In here we are going to work with X and Y plane. So then simply you can understand these component and this part need to go 0. That's happening here. So you can study from this part. And again, you can rename this one as a tau, and this is how again I'm going to explain this one again. These we call the normal stresses, others we can define as shear stresses. And you know the definition is stress, and this is a plane and this is a direction. Okay, this is a plane and this is the direction. Okay, so now again you can put in this manner. This is actually our general element. So we can come to here. So next one about like this one, we know the complementary theory about shear stress. These should be equal, otherwise it's not going to give equilibrium system. So now we can simplify this one. Actually we don't need to put this way. If you like, you can come with this way, that's enough. Okay, tau xy, and this is our general element. If you are going to do any stress element arrangement or analyze, you need to keep mind this element and you need to map our target stresses to this element, and after that you can start work. I will show you this kind of example. Okay, now you can keep the idea. So what we are going to do, so now we're going to work about like a plane stress analysis, and we are narrowed down about our stress and to plane stress problems, not to plane strain problems. So plane stress definition you know now, and plane stress general element or the general element. This is actually the general element. Okay. Now we can go a little bit about this one. Now this is our transformation. Now actually I am not going to explain again and again. Transformation means actually simply what we are going to do. What we are going to do from one axis to one axis system. This is our axis system x and y. To we are going to transfer another axis system simply our stress component. In the plane stress problem, we need to find actually three components, just three components. One, two normal stresses and one shear stress component. So two normal stresses and one shear stress. So any plane you need to find these three things, what going to happen. Okay, that's the thing we are going to study under this transformation of stress section. So now, okay, this is again give the same definition, you can see. So in this section we will show how to transfer the stress component from one orientation or one coordinate system. This is our coordinate system to another coordinate system. This is our general arrangement and this is our target arrangement, theta rotation. And when you come to the here, so the books and other things some kind define there were different sign convention and different rotations. But in this course we are taking anti-clockwise as positive rotation. So our angle or our element we going to rotate in this direction, anti-clockwise, opposite to clockwise direction. So this direction we are taking positive. If anything in this direction we can consider as a negative angles. Okay, so this is our target system. This is our given system. This is our target system. These are the things you need to find. Okay, these are the things we know. From this one we need to find this. Simply that's the thing. Okay, when you come to the here now, so this is our stress element. So now I'm going to get like a wedge, of course, as it is. So also we can analyze, but I like this is my point. I put the point then so easily you can visualize. This is my point. This is a arrangement. Okay, this is if this point, if you have like this kind of cut, the stress are like this. If we have this kind of cut, stress like this. Now I need, if we have like this kind of cut, it don't need to have a theta, any angle. Okay, any angle is fine. Sorry, wait a minute. So any angle is fine. Any angle is fine, like this type of any angle fine. Okay, so it don't need to be diagonal one. Okay, so think however that angles theta, so this should be okay. You can see now that means my normal is I am interested about theta rotation. Okay, theta rotation is a positive one. Okay, in here I'm give the definition for my tau. That means like a clockwise positive. That means this is my target phase. I am putting this one to create clockwise shear. Clockwise shear. Okay, some of the book, especially in your American textbooks, what we are using, they are using in this direction, opposite direction. Then, of course, they will end up with different sign. Okay, only quantities wise same, the value wise same, but sign will go to the opposites. I will show later. Actually, that's thing. Now this is our arrangement. Okay, think. This is my arrangement and I am interested about this here and need to find this one and this one. Okay, this is a plane. Okay, this is our in my interest plane. And to get, oh, of course, this is something we are going to work with like equilibrium equations. So now I am getting like a portion of this one, wedge of this one, and I am putting, and this is actually free-body diagram of this one. And the rotation of theta, okay, I get like angle theta cut, so that means like here creating normally stress for the given axis for theta. That means actually I am rotating theta. And now I'm going to take equilibrium for two direction means x and y direction. Sorry, x and y means the now different this one. This is my x dash and this is my y dash. So I am going to take equilibrium in these two axes along these two axes. So think about this area dA. Okay, this area dAx and this area day. You have stresses, you need to force, so you know you need to multiply by area. If you have dA in here, so this is a rectangle triangle, so you can define dAx and day by using this theta. Okay, this is a way. Okay, first I am going to take equilibrium. So equilibrium along this axis, that means like a normal axis. Okay, this is tau n part, tau n direction. So now simply what you need to do, and you need to take all the component along this direction, forces, okay, not stresses, forces. Just you need to multiply by area stress, you can get the force, and you need to sum up. I'm not going to do this one, please. You have enough time, so please go through this one and try to understand. Okay, these are the forces that will come from this line. And now you can know dAx. I can replace from, sorry, this one dAx, dAn, day also we can replace by dan sine theta. So replace this thing, you will end up with this, and you have this triangular relationships. Okay, triangular relationships. Now you're going to introduce this relation to here. Cos square theta is equal to this one, cos sine square theta is equal to this one, and sine theta cos theta, 2 times sine theta cos theta, you know, it's like a sine 2 theta. So you're going to introduce this one and you will end up with this simple equation. This is the variation of normal stresses with theta. Theta is rotation angle in the clockwise direction. This is our x. We are started from x, okay, general x, so that's also important. In here we are measuring our angle from here, okay, here to here. This is theta. Okay, very simple. This is fine. Now this is you can take out. Same way you can take the equilibrium along this axis and you can get the equation same way. Then now you can see sine theta cos theta, sine theta cos theta, those you can replace by this one. Cos square theta, sine square theta you can replace by this one. You will end up with this equation. The equation 1 and equation 2. Equation 1 give the variation of normal stress is theta. Others are all constant, rather than constant, you know, sigma x you know, sigma y you know, tau xy you know. This is a theta variation, and this is tau n. shear stress variation with theta, tau component. Okay, so simple two equation. Of course you have cosine part, but it's very simple. Okay, now we go a little bit more about this one. So now think about what is actually this. So we are going to test our equation. Okay, so this is the equation, this is the equation. So now I'm interested about when theta equals 0. Actually we know when theta equals 0 you need to end up with this arrangement. Okay, this is the given arrangement, this arrangement. We will see it happen or not. So theta equals 0. So what going to happen? Theta equals 0. This is going to 1 and this is 0. Okay, this is 0 and this is equal to 1. Due to 1, this part is going out. It will end up with tau x. So sigma x, that is x part. And same way you can apply to 0 component, then you will end up with this 0. And here you end up with minus tau x y. Careful about direction. So this is the way. Now we know the minus means it should be created. We are targeting x equal t. So theta equals 0. That means this is our line. So target reference line. Theta rotation. So the plane should be this. So that means actually we are interested about this plane. And we end up with normal stress sigma x this direction, and this plane need to give opposite of tau. That means actually the positive tau means it will create clockwise rotation, but in this means it give the anti-clockwise. That means it should be end up in the other direction. Okay, this is the way. And of course if you put it like a without sign part, if you're using these two things, then you will end up with this one. Okay, and same way you can check with this phase also. Okay, when you come to this phase, what you can see, theta should be need to equal 90 degrees. And then simply please apply this one. You will end up with these values, of course tau creating positive, so that means end up with same value. Okay, same value. And this is, if you use this notation, you can replace this one by this way. So very simple. Now we have confident about these two equations. These two equations it working. So actually this is a way of actually cross checking these equations. So you can put what you know and you can check it is working or not. Of course we know it should work, but you can get confident about the equations what we developed. Now we can see a little bit more about this one. So this is a transformation system. So now you know this is our real element and this is our given element, and we are interested about this kind of arrangement. The given axis x and y dash, sorry, x and y, and we're going to transfer this one to x dash and y dash. Think about that way. These equations are usually called transformation equation for plane stress, because of course plane stress we are working with plane stress, because they transfer the stress component from one set of axis to another set of axis. This axis system x and y, this axis system x dash and y dash, rotation with theta. Okay, so now think about these things. X dash sigma x dash, so it should be equal to this value, so theta. And when you come to this arrangement, so this is theta equal theta. Okay, when you come to the y axis, it should be, you know, theta should need to equal theta plus y over 2. Okay, so this is theta plane, and this is theta plus y2 plane. Okay, so simply you need to understand those arrangements. Okay, so now you can get these from these simple equations. These simple equation you can get out these results, and these are the arrangement. Tau n, of course we have a Ln value, Actually tau I will replace, of course it's better to replace this one with this manner. So tau, actually this is x dash y dash, that's the best name to this one. Okay, yes, these things I already explained. We need to find two normal stresses and one shear stress. Okay, these are the three components that we need to find to complete our element components. And there is another thing what we can see. So now think about just addition, just addition of these two equations. So then decide what actually we can see, sigma x dash y x dash, this is here. And if we are going to add these things, this is going out, this is going out, and this part going out, this part going out. Here we can see sigma x and sigma y is coming here. So what you can see in here, we can see the addition of normal stresses of given element of any orientation of element is a constant, and it's not going to vary with our axis system. So those kind of values normally we call the invariant, and this is with respect to coordinate rotation. So any coordinate rotation addition, okay, not individual values, okay, addition of x and y, or otherwise we can call these normal two stresses give constant value. So these kind of arrangement or these kind of values we can define invariant. This is with respect to coordinate rotation, and keep in mind again, individually these are not going to equal, okay, not going to equal. Okay, so individually of course they are varying, but the addition of these normal two stresses give constant value. It's not going to depend on your coordinate rotation. Okay, so these are something important when you work with like some kind of special problem, so you need to keep in mind. So now we can shift to a little bit more detail. Of course, yes, you are correct. So these two equations enough to work, yes, but in this one I'm going to little bit more modify this given equation using some geometric represent, because this one same time the next session of this one, what I'm going to do, I'm going to explain this one from Mohr circle. When you come to the Mohr circle, it is has a some like a geometric dimensions. So now what actually I'm going to do, same equation I'm going to remodify or rearrange by using that geometric parameters. As it is, of course, you can use, no problem. You can start this one and you can solve it. And this is just modifications. Okay. Now again, I'm going to shift to triangle, right angle triangle. You know about this one. So I'm going to define here as 2 theta, 2 phi actually, 2 phi. And this value, I don't know. I'm putting this value only, not a sign value, and this value as this way. If we have these things, you can find R as this manner. So that is straightforward, and same time you can define this 2 phi and 2 phi by using sine, cos, or otherwise tan 2 phi. Okay, don't ask about why I'm using 2 phi rather than phi, because there is a meaning. I will explain later why we are using 2 phi rather than this one. Now what actually I'm going to do, I'm going to remodify this equation. You can understand in here normal stresses, I can play with this one and I can get the R out from this one. Okay, R out on this one, and I can remodify. Here also same, I'm going to get R out. Okay, so then you will end up with these type of arrangement. So you know the definitions. Okay, you know the definition of cos phi and sin 2 phi, and after getting R out, you can see here we can see cos 2 phi, and here we can see sin 2 phi. And this one, you know, cos sin, that means like a cos minus theta. Of course, this is a 2, so cos 2 theta minus 2 p. You will end up with this equation. And same thing happening here. This is again minus, and this is cosine, cosine, cos. So this is from A level knowledge, it should end up with sine. So now you can see very nice arranged two equation. Yes, it is correct. So you can use this one, either set of this one, up to you. In here, before you use, you need to find r and theta, so phi. In here, you don't need to find anything, you can straightforwardly apply. And here, you need to find r and phi to apply this equation before any other calculations. Okay. So there's an advantage also. You know R and phi. I will explain what is the R and phi, the definition. Actually, what is a physical meaning of R and phi. I will explain these things later. Okay. Now we can go a little bit further. So now I am going to use, of course, you can plot these two equations. Should give the same. No, I am actually going to play with now these modify two equations. Same. It's not going to change. Just I am going to plot now this normal stress with theta. Phi is a constant. Okay. Phi, you can see it is a defined variable. R is constant. R for given element is a constant. Because of these are known values. These are known values. So R is a known value. And for given element, these are constant. So R is constant for that particular element. If R is constant, so you can say cos 2 phi, somehow 2 phi or phi going to give like a constant value. So that means these are fixed values system. So what actually we are going to do here, we are going to play with normal stress and theta, and tau shear stress and theta. So same in here. Okay, here same now. So this is only theta n is a function of, normal stress is a function of theta, and tau n shear stress is also again function of theta only. Okay, there are no any other things. Okay, for given element. Okay, given element. Now we're going to plot it this one. What's going to happen? So first we're going to plot this one, normal stress. So these are the known values, and you can see when you come to plotting this one, this is cos variation, and it's a 2 cos variation and amplitude with R. And yes, of course, this is they have a shift to equal this much value. So that means the normal axis or the symmetric axis should need to shift to this much. So that's why this value is here. Okay, and after that, what just you need to do, you need to just plot this value. You can see, and here when you come to the plot, until to phi we call the phase angle, there is a phase shift. We call the phase shift. So we can call this one to phase shift. Later we will, when you come with geometric representation of these things, so they will give these things, we can give the meaningful names later. Okay, so R also same. Actually R is a radius for that curve, but I'm not going to use now these things. Okay, so just plot it. So this is, we can see in here, we can see clearly there is a shift. We call the phase shift. From your A level knowledge, you know these things. And from this one, you can see again cos variation here to here. Okay, and this tau variation or shear stress variation also same. There is no change. Actually, start again here. We can see it like a phi shift, phi amount of phi shift, and after that it's going to give the sign variation. Okay, and now I am going to interest about, of course, plotting is nothing, so you can use Excel and you can plot it and you can check it. And now I am going to check the most important thing in here. So come to here, pen, and this one we can see the maximum. Of course, we can see the maximum points and minimum point of this normal stress variation. Okay, when we can see the maximum, so the very nice, there is a very important thing. We can see shear stress going to 0. That means when we can see the maximum normal distress at that plane or that direction, normal distress gives 0 value. It happened to minimum also. This is a minimum normal stress. At that time also, what we can see, our shear stress going to 0. Here also happens same thing, shear stress going to 0. Okay, these planes, the maximum, where we can see the maximum and minimum normal distresses, these plane we are going to give special name to this plane. We call the principal planes. Okay, principal planes. These stresses we are given the different name now. We are going to call for this thing principal stresses. And here we can see two principal stresses, maximum and otherwise we call the major and minimum principal stresses. So major principal stress we are going to give sigma 1 and minor principal stresses we are going to give the sigma 2. So where we can see sigma 1, if we can rotate our system, or we are starting from here, no? If we can rotate this system to phi, amount of phi, we can see first principal stress or otherwise major principal stress. In here you can see clearly. When we can going to shift, or when we can get to, when we rotate our this plane to phi plus 90, so that means for this for 90, okay, we can see second principal stress or minor principal stress. Okay, at that planes or these planes, tau is equal 0, no tau, no shear stress. That's the most important thing. Okay, and same time you can check other way. So when you come to check maximum tau positions, this is tau max we call, and this is tau mini. Value wise same, okay. So value wise this tau max is going to equal R and tau mini is going to equal minus R. Value wise is going to equal to R, okay. R. At that time our normal stress of that part not going to 0 because of this has a constant value, okay. So shift of axis. So because of that it's not going to 0, but the value is we call the average value. Sigma average, AVG, average. Okay. So at that time our plane, okay, rotation is equal to this much. I will show you, explain clearly in the next few slides these things. If we can rotate our this plane to, this is theta phi, sorry, phi rotation, phi first 45, we can see how max direction is in here positive. Positive means the plane need to give like a clockwise, and this is tau max, and normal stress in here. So you can see it depends, the positive or negative depend on these values. So however in here we are given the positive values. This is tau average. I will show this thing, don't worry about this, my drawings, so I will show you clearly. This is the most important thing. So here we are going, we now you know about like what is the principal planes and principal stresses. We can define two principal stresses, sigma 1 and sigma 2, major and minor at that time, at that plane. So we cannot observe any shear stress. Otherwise, like when we can see the maximum tau, of course we can see tau in here, and at that time shear, or sorry, normal stress not going to 0. Okay, it has values. Okay, now we can shift a little bit more, and this is a definition. I already explained. The maximum and minimum normal stresses called the principal stresses. and this is a major principal stress. Sigma 2 we can call the minor principal stress, where we can see this one theta equal phi and theta equal phi plus 90. So at that time this value going to 0, and the value of course, okay, I need to show this one value. Of course you can see average plus r, average plus average minus r. Okay, so there's a very nice arrangement. That's why you actually rearrange these equations, otherwise of course you can work with these things, no problem. And here this is our given element. Now if we can get like a p rotation from this our given x-axis, we can see our principal plane. This is our first principal plane. This is our first principal plane. That time tau going to 0, no shear. And second principal plane, we need to add more phi plus another 90. So again tau going to 0. So this is an arrangement of principal stresses. Okay, principal stresses. So we can go further, and this is of course the whole idea about these variations. Okay, here we are. This is our arrangement. Okay, this arrangement, given arrangement, and if we can rotate this axis to phi, you will end up with first principal axis. Sorry, first principal plane. And if we can add more 90 for this one, so you will end up your second principal. This is major, this is minor. So if you can apply phi plus 45 angle, you can see tau max. So the direction, how you're going to define the direction, so you can go to here, tau max here, positive. Positive means is need to create clockwise rotation. So that's why it is in the clockwise direction. And the normal stress here is given as a positive. So it's the value. This actually we can show this is a sigma average. Average. You already know this is not going to vary x and y addition for any rotation. You know now it is an invariance value. So that's why we can define as average value. And for 90 for this one. So this is our axis, 90 for this one. You can see the minimum value. Of course, the maximum or minimum both are same in here, value wise same, only the direction going to change. So when you come to the here, in here, you can see value same r, only things like a direction. Here direction negative. Negative means it need to rotate anti-clockwise direction. Okay, so that's why I am putting anti-clockwise direction. Okay, anti-clockwise direction. So this is the arrangement, whole picture about these variations. So when theta equal this much, you can see the tau max. So that's clear, and that's equal positive r. And theta plus another 90. So you can see minus r. This is a minimum, but values are same. Okay, r, that's the r. Another one you can take out from this one. If you're going to add these two equations, what's going to happen? Check it. Actually, rather than adding, so I'm going to subtract sigma 1 minus sigma 2. So then what we can see, it is going to equal 2r. So then r equal sigma 1 minus sigma 2 divided by 2. So another, all are some kind of arrangement, so you don't need to worry. If you know the sum one things, that is enough. Other all are like a mathematical rearrangement of the equations. Okay, so now this is actually we expect the variation with our stress, normal stress, and shear stress with rotation angle or given angle. So that's the things actually we expect, and we got it the variation. This is actually one way of graphical interpretation. For the next section of this one, we're going to represent by using more circle, that is give more clear idea about the variation with sigma and tau, the combination of sigma and tau. Okay, now to get clear idea about this one, we can shift to example. Okay, I will try to explain one or two example in this section. So the first example, so just read. This is your first example. So okay, plane stress condition, load structure where the stress having the magnitude and direction showing block. This is our given block. Okay, this is the given block. Okay, this is after that actually I already explained our all the this keep it. I will shift it with this one. Okay, this equations, okay, okay, I will read too much things. This equation and this equation we derive from based on this stress arrangement. So that's why we are using this as our actually general stress or reference stress element. So what you need to do, if you have any example, you need to plot first or map your stress for your general stress, your general or your reference stress element. So okay, we will plot it, and what they actually the block, and we are going to rotate this one counterclockwise. That means actually 15, that means it's a negative. Okay, we are going in the 15 minus 15 negative angle. So how about the stresses? So very simple, and we know how to do it, but very carefully we need to understand procedure. Okay, so this is the given one. So we can see this arrangement, but this is our reference stress arrangement, reference element. So first we need to plot for this one. When you come to the here, okay, this one find this direction, and you our reference stress shear stress arrangement in this direction, and that means this one should be minus to here. Okay, minus to here, and this is again in the reference one in the tension side, so that means again this is compressive, so because of that again minus. This is tension, this is okay. So these are the value. Then sigma x, so it should be minus 46, and sigma 1 it is 12, it's correct, positive 12, and sig tau xy minus. This is your given system, this is your, you going to plot it or you going to map for reference system, this reference element. Okay, now we're going to play with these values. Just actually you need to do, you need to substitute this value for your equations, just nothing. So you can use either this set of equation, this one and this one, or either these two things, up to you. Okay, you can use any of these equations. Okay, now you have a components value. So we're going to rotate clockwise, that means like a minus direction, keep it mind, so minus 15 degree. So and that angle, what going to happen to your stresses, that's our problem. So when you come to here, just in here I'm using the basic equation, not a modified one. You can use anything, again I'm telling again and again. So just use this equation, substitute. So now this value should be for reference element, okay, from this one. Okay, this value from the reference element, just substitute, you will end up with your value minus 30. That means like this is a compressive, and sigma 1, that means when you come to the sigma y, what you need to do, you need to add 90, actually 90 plus theta in here. That means 90 theta equal minus 50. That's why it is come like a minus case. Okay, minus 50. Okay, so in the 2 time is there. So finally you can end up with your perpendicular line also. This is for x and this is for y dash, and this is x dash and this is for y dash. And the next one, tau, again same, I'm using the fundamental equation, and just add it and you will end with positive. So now come to here, this is compressive, you have 32.6 is a compressive. So now I am rotating this our angle for this direction 50, and this is give the minus 32.6, and we are marking this one. And the perpendicular, of course, it should be, if it is a 36, this should be in the minus 36. Okay, so we don't need to find those things, of course, because of this equilibrium now. So just you can target one, you can mention one value, that's enough. And when you come to the here, again this one, again the minus 1.5, you can mark it. And this is a little bit tricky, so you need to think this is positive 31. Then we are talking about like every time the x rotation. So that means we are interested about this plane. Okay, this plane. The given we are going to target, or we're going to mark for this plane. Okay, x plane. So then this is positive. Positive means it should be clockwise. So that's why it is in the clockwise. If you know in this arrangement, you know the complementary component should be come in this direction. To balance this one, there should be this direction, and this way to balance this force, it should be this direction. So simply you can finish your element arrangement. So very simple one, very simple one. Again I am telling, so this is the step. This is the most important step. Mapping of your given element stresses for your reference stress element, and after that just substitute, nothing. And we can shift to second one little bit what they are asking. Of course, given stresses are these things. Okay, given stresses, following determine the principal direction and principal stresses and maximum the basic things. When you come to here, just again what we do, we need to plot it, or you need to map it for these known values for your preferred element. And after that, please get these values. For this one, this is compressive, and this is a tension. This is the again tension. We don't need to cherry, and this is tension. This is T. We don't need to change. And here again, this is opposite, and this should be minus. That's all the thing. And now we are interested about to get like a principal direction and principal stresses. So from equations, we know where we can get it from these things. So we can see where we can see. I will remove this thing very. And where we can see, and the principal values, first value we can see if we can find the phi at the phi angle or phi plane, and the second one we can see phi plus 90 angle. So these are the things that we need to find if you're working with phi, or otherwise you can work with the general values of theta also. Okay, so now we are going to here. So second example. Okay, so these are the directly I'm going to use this equation. This is the equation from graphs. Okay, so you can see this is sigma 1, and this is sigma 2. Okay, so sigma 1 this one, sigma 2 this one, x you know, y you know, you need to find the r. So to find, you know the equation to this one, so you can just put it this equation, you will end up the value. So that means sigma 1 and sigma 2 is straightforward, you can find it. But the problem is like a direction. So when you come to find the direction, so we need to solve these two equations. Otherwise you can work with tan to theta also, to phi also, no problem. But I like to work with these two things. So we know the definition of cos 2 phi and sin 2 phi. Cos 2 phi is this one, sin 2 phi is this one. So you can substitute these values and you end up with minus some value, and this is also minus some value. So now I'm going to again to your A-level knowledge, so you know the quadra. So in here, if you have this quadra, you know in this first quadra you can get all tan, sin, cos positive, all are positive. In here sin positive, other two was negative. And here tan positive, other two are negative. In here cos positive, other two are negative. Okay, so here you can see we need to find something cos and sin negative. So that means we need to work with quadratic. Okay, so if you're going to put this value for your calculator, and it will give the value like this, because normally in the calculator they are giving their range is 0 to 180 for cos, because of it going to cover positive and negative. Okay, so positive and negative. And for sine, give the same this value because the variation give the 90 minus 90 to range is minus 90 to 90. So it's going to cover positive and negative parts. From these values you cannot estimate. Of course, these are different values. You cannot estimate, but we know somehow there should be value within this range because of its vary. Somewhere we can find cos and sine to lie in this third quadrant. So to get it, you need to shift to, or you need to refresh your A level knowledge. You need to shift to general solution for sine. This is your general solution. This is n is like any positive integer, so you can apply. When n is 1, what I can see, some value 256. Okay, that is means this one, or otherwise if it is not, you need to rechange 0, and you can try with 0 and 1 and 2 something, and it need to be give something third quadrant thing. Okay, so I need to check with other one also. Then we come to here again. This is a general, so it should be this one. Sorry, degree should be degree. And again, when you come to 0, so of course, then we can see it can come in minus 52. Sorry, minus 140. That means it is come from this direction here again. That is third quadrant. Okay, so that means this both are same angle. Okay, this is a positive waves and this is sine wave. So that means we can use this as our this solution for, or pair solution for this phi angle. So phi angle we can use 128. Okay, so otherwise we can use minus 52, minus 52. Okay, rather than this way, so it is better to go with 2t now. So 2 phi, so 2 phi, better to go 2 phi. 2 phi equal 256, or otherwise minus 104. So this is we are going to find actually to general solution, so fair solution for 2 phi. So that is okay. So then you can go with this one, and that will end up with p equal 128. Okay, 28. So this is a way of calculation. So first you need to identify, otherwise you can play with the tan. That's also, however, you need to find pair or p2 phi for 2 phi for this system, and after that by using 2 phi you can define the theta. Because of our first principal angle for phi 1, we can see theta equal phi, and second one we can see theta equal phi plus 90. Okay, this is a way of calculating these things. Okay, no problem at all. And now we know the values, so we will go to here. So you can see first principal direction 128. From x to 128, you can see first one and first one, and from this one you need to add another 90, so it will end up 280. So 280, you can see your second one. Okay, so after that you can generate this accesses. Sorry, this is actually, sorry, this is more important. Don't miss up this thing. So this is our TP1 plane, and this is our TP2. Okay, TP2. Now you can draw your element a line with these things. This is parallel to, this should be parallel to y second one, and this should be parallel to first one, and these are the directions. Okay, axis direction. This is line with this one second one, This is second plane in line with this one, so it's a compressive one. So you can see, okay, here, so this is a compressive one, and this is 4 point something, so compressive, and this is positive tension one. So this is here, this is compressive. Okay, so simply that's the end of the two example. Sorry, that's the end of two example. Simply here also, what actually we are doing, the given system is here. Given system is here. First you need to plot it, or actually map for your preferred element, and after that identify the parameters, and next things how to use your equations. So just applying this equation, and here when you come to find your angle, little bit careful, you need to think about to get like a fair solution. So then you need to, if you work with like cos theta and sin theta, you need to find the general one for these satisfying these cos and sin components. When here it's come to quadratic, when you come to the quadratic, you need to use the general solution of sine and cos, and you need to find the solution for that, to give like a general or fair solution for these two cases. And after that, this interpretation is more important. So you have x and y axis. When you rotate this one 128, you can see first one, and when you rotate 128 plus 90, that means like a 280, you can see second one. So, and after that, based on that, you can develop your element. Okay, and here again I'm telling, this is of course tau max also you can find without trouble, that should be r equal this much. I'm not going to explain these things. And here, more important, we cannot see tau at this stage. These are principal levels, principal stresses at that level we cannot see. Okay, so this is the end of this section about stress analysis. Here we are used equation. The next section I'm going to explain about geometric interpretation of 2D stresses, same plane stress problem, by using Morse circle. Okay, so, and I will show a little bit further. Sorry, wait a minute. So actually these two also I will upload, and this is again reading materials, you don't need to worry at all. Okay, so you don't need to worry at all for these things. Sorry, I cannot see this one. Okay, so you don't need to worry, or just keep it and just read. This is for plane stress variation, plane strain problems. Okay, this is for plane strain, and the formulation is also there. So all the formulation, it is clearly explain everything how you're going to formulate. Like this is for plane, how you formulation for plane stress problem. This is for formulation plane strain problem, and this is just reading material. You can read and you can get how when you go to work with plane strain problem, how you going to work. Okay, that's the only thing. Go to here, clearly explain in these things, and I will upload these things, and you will end up with equations like this. When you come to the plane stress problem, you can see normal strain variation, and a stress variation. This equation you already know now from our plane stress problem. This is plane stress problem, and this is from plane strain problem. So derivation, of course, from this note you can take out. And when you're going to compare this one, you can see plane stress and plane strain. We are going to work with normal stress. Here we are going to work with normal strain. So you can see normal strain. So equation is almost same. Only thing you are going to represent or replace normal stresses from normal strains. That's the only thing. This is sigma x. This is epsilon x. This is sigma y, epsilon y. This is tau. This is tau shear. This is gamma shear strain. And the only way change is here we can see 2, but here we cannot see 2. That's the only thing. And when you come to the here, again here we can see same changes, but here we can see the minus is here. Minus here, half of that. Again, we can clearly see when there's a shear component, we need to multiply by half. This you don't need to remember those things. Okay, yes, I'm showing like the analogy of these to analyze. This is for plane stress, this is for plane strain, and you can simply you can go to this one, you can get the idea. And this handout again explain about geometric representation of plane strain problem also, so you can leisurely read. And again, of course, I'm not going to check this one, this plane stress part, so plane strain part in the exams. Okay, and the next one about the sign convention, this also I will upload. This is from your textbooks, and here actually when these are already you know now, this is a plane stress and plane strain condition, so you can read it. This again extra reading materials. And when you come to derive the equation, you can see this sign convention, they are using arrow in this direction. Our case we use a downward direction. Okay, so keep in mind that one, a downward direction, because they are using different sign convention. So here we can see sign convention. So tensile normalization, that is correct. Anti-clockwise, so shear stress positive. So anti-clockwise shear is positive. That's why they are giving it this upward arrow. Then they will end up with, actually this is again same as our case. You can see same as our case. This is similar to our case. But when you come to the here, you can see the sign is changed. Here minus, here positive. Our one, it is opposite. This is positive and this is minus. So carefully, the values are same. Only when you go to plot it or something, it will give the opposite directions. Okay, I am putting all these information for fields because you should know. This is not for you confuse, but you should know this is just for sign, playing with sign and directions. Okay, different countries use different sign convention, especially Americans use different sign convention compared to our system. So, but you should know how to refer any books, so you don't need to surprise from looking at those things. Okay, now this is the end of this one. So next video lecture will cover geometric representation of this one. Until that, so thank you very much.